I'm a senior lecturer in physics, and my research is in surfaces and interfaces. And so I'm going to talk to you today about solar power and carbon capture. So just to give you an outline of what I'll be talking about. So we're going to talk off just discussing the energy problem, how we need some new greener energy solutions. Then I'll talk to you about my research area, which is surface science, and why surfaces are important. Then I'll tell you about ionic liquids, which are a type of material that have lots of applications, and I've been using them for the applications of CO2 capture and for solar cells or photovoltaic devices, as they're also known. And then just a bit of an outlook at the end about the future of these devices. So to start with then, so we know that CO2 emissions are increasing and that this is contributing to global warming. So if we look at this this chart here, let's see if I can get a laser pointer up. So looking back to like the 1950s, we can see that CO2 emissions were obviously a lot less then. And the main contributors were America and the European Union. But in the last sort of 70 years, going up to the 2020s, we can see that actually the European Union and the US contributions maybe haven't changed too much, but the rest of the world has now started producing a lot of CO2 as well. Particularly places like China and India are now big polluters as well. So obviously, we want to try to do something about this. So we need to move to cleaner energy sources. So this picture here is actually a picture of Fiddler's Ferry power station, which is one really close to where I live in Warrington. So this was a coal-fired power station, and it was one of the most polluting in Europe. This was shut down a few years ago, and they've actually started demolishing all the cooling towers now. And so the UK now doesn't have any coal-fired power stations. So the last one, which was in Ratcliffe-on-Soar, closed down in 2024. So we no longer have any coal-fired power stations. So we do still use natural gas, which is a fossil fuel, and so that's still producing CO2, but it doesn't produce as much as coal. So obviously the UK, we are looking to move to cleaner energy sources, and we now do get about 30% of our electricity from wind power, and there's still lots of onshore and offshore projects sort of in process at the moment. So this is still an expanding field. Then obviously nuclear, we do get some of our power from nuclear, so that is around 14% of our energy supply that we get from nuclear. The government are looking to invest in this heavily, so they are now looking to invest in decommissioning, and so also things like small modular reactors and advanced sort of technologies that are going to help us to increase our nuclear energy supply. So obviously this is a little bit controversial because some people, obviously it produces nuclear waste, which isn't ideal either. But then, you know, if we don't want to produce CO2, nuclear is really at the moment probably the only other option to give us, you know, the power that we need to power the UK. Then we do at the moment get some of our energy from solar, so that at the moment is only about 5%. But there has been a big increase in people getting solar panels put on their houses. So that's partly due to government grants to install these. And the installation costs are coming down a little bit as well. And then there's also things like biomass, which we currently use only a few percent of our supply at the moment. So that's basically like burning like bio waste. So you can either burn it directly or you can try and convert it into fuels that would be useful. So today I'm going to be talking about how we can capture CO2 that we are emitting. And I'm also going to be talking about solar energy. So I'm going to have a little bit of a detour first and tell you about surface science. So this is the sort of area that I am interested in. So you might be thinking, what's so exciting about surfaces? Well, there's a physicist called Wolfgang Pauli, a famous physicist, and he said that God made the bulk. So this is the bulk of materials. The surface was invented by the devil. So basically, everything goes a bit crazy at surfaces. So in the bulk of a material, so if you just have a slab of material, anything in the bulk, you kind of look around and that atom is going to experience, it's going to look the same everywhere. So whichever direction that atom looks in, everything's going to look the same. Whereas if you now look at an atom that's at the surface of the material, that sort of periodicity that it would see in the bulk is now broken. And this is where all the physics sort of then goes a little bit crazy. And now this surface is exposed to the environment. So whether that's air or whether that's another material, if this is like a layer of different materials in a device, perhaps. So basically, this is where all the kind of interesting physics happens. And if what happens at the surface dictates whether that device is going to be successful or not. So surfaces and interfaces between materials are, really important subject to study. So when we look at surfaces, we tend to carry out these measurements in what's called ultra high vacuum. So atmospheric pressure is 1,000 millibar. So there's different units of pressure, but if we're doing it in millibar, then atmospheric pressure is 1,000 millibar. We do our experiments at about 1 × 10⁻10 millibar. So that's like 13 orders of magnitude difference. So what we're trying to do here is we've got a big metal chamber, and we are trying to get all of the gas molecules out of that. And so the pressure gets so low that it's almost getting as low as the pressure on the moon. So we've really taken, the majority of molecules out of this chamber. And so the reason why we do that is because if you have a surface and you just hold it in air, it's going to get contaminated really quickly just by things sticking to it. And that happens very quickly and on the order of like nanoseconds. So by putting it into a vacuum, there's processes that we can do within the vacuum to get that surface atomically clean. So there's literally nothing on the surface, and it will then stay clean. And then we can deposit things that we're interested in onto the surface just to try and understand the physics between these different materials. Another thing is that the technique that I use requires me to measure electrons, and electrons don't travel very far in air. So if you had electrons in air, they just get scattered very quickly and you've lost them. So if we want to measure those, we need to do that in vacuum. So this is called a short mean free path. So electrons have what's called a short mean free path. It's basically how far they travel before they get scattered. So, and then also some of the equipment that I use, it can only be operated at ultra high vacuum anyway, because they've got these delicate filaments that would burn out otherwise. So this picture here is actually a picture from Diamond Light Source, which is a synchrotron, which I'm going to tell you more about in a minute. And you can kind of see there's a series of like pumps and various things on there that help us to remove all of the gas molecules from the chamber and to get it down to ultra high vacuum. So as I said, I tend to do experiments at synchrotrons. So these are big particle accelerators. And so normally when you think of a particle accelerator, you might think of something like CERN, where you are smashing particles together and seeing what comes off. But what we do is we are sending electrons round in a circle, and they give off radiation when they do that. And so it's the radiation that we're interested in. So what happens is you start off with some electrons here. They go down the linear accelerator and into this booster ring where they get faster and faster and faster. And then they go into the storage ring. And as they go round here at close to the speed of light, they get bent round in these bending magnets. And as they get bent round, they're sort of essentially they change their acceleration as they get bent, and that produces synchrotron radiation, or sometimes known as Bremsstrahl lung. And then this radiation comes down these beam lines, as they're called, and it comes down a series of optics and various other things, which allows you to sort of tune the beam. And it goes through a monochromator, which allows you to pick a particular photon energy that you want for your experiment. So synchrotrons actually give off a whole range of radiation, all the way from the infrared to hard X-rays. So generally, when you go to a synchrotron, it's the X-rays that everybody is using. So you get these really intense X-rays, which allows you to take measurements very quickly because you've got such an intense source of X-rays. So what do these synchrotron facilities look like? So they kind of look like big UFOs, and they've got these all over the world. So this one is one in Grenoble in France, which is very pretty in the middle of the Alps. This one here is Diamond Light Source. So this is the UK's synchrotron. The UK's synchrotron used to be in Warrington at Daresbury Laboratory. When I started my PhD, that's where I used to go to do experiments. But they have now built this brand new one down in Oxfordshire called Diamond Light Source. Then they've also got one in Sweden I've been to. This one's called Max 4. This is near Lund in Sweden. And then in Denmark, they've got a very cute synchrotron, which is a very tiny one, and it's under a car park in Aarhus University. So this is the physics department of Aarhus University, and they've got a synchrotron in the basement, which is pretty cool. And I might be going there this summer, actually. So these are what these synchrotron facilities look like. So in terms of the measurements that I actually take when I go to these facilities, so I use a technique called X-ray photoelectron spectroscopy, or XPS. So this is actually based on Einstein's photoelectric effect. So I think during your A-levels, you might have learned about this. So this is actually what Einstein won the Nobel Prize for. So what happens is we get the X-rays coming in from the synchrotron, and we've got our electrons here, which are in these energy levels. And then this excites an electron out of the material. And this electron will have some kinetic energy, which we can measure using an analyzer. So we've got our X-rays coming in, we get our electrons coming out, and we can measure those. And then from that measurement of kinetic energy, we can actually work out the binding energy of the shell that it came from. So that's because we know the photon energy, we know the kinetic energy, and this is something called the work function, which we can also calculate. And so once we know the binding energy of these electrons, we can actually work out what materials we have, because depending on whether you've got, say, carbon or oxygen or nitrogen or whatever atoms you've got, each atom will have its own unique fingerprint of binding energies. So once you measure the binding energies, you can sort of pinpoint which elements you've got in your material, and more specifically, which elements you've got at the surface of the material, because this technique is highly surface sensitive. So this is again because of these electrons having a short mean free path. So because they don't travel very far before they get scattered, it means that we can only detect the electrons coming from the very top layers of the material. All the ones from below just kind of get scattered, and they just kind of contribute to this kind of background noise that we get. So you only actually detect the electrons from the top few layers. So it's a very surface sensitive technique. And not only can we work out what elements we've got, we can actually work out how they're bonded to other things. So, for example, if you had like an oxygen atom that was in a water molecule, or you had an oxygen atom that was in some sort of metal oxide crystal, because that atom is in a different environment, you get these small shifts in your spectra, which you can fit, and then that will tell you what kind of environment the element that particular atom is in. So from that, you can actually work out how things are bonded. You can put molecules on a surface, and you can work out how that molecule attaches to the surface. And then there's a related technique that we do that actually allows you to work out like the orientation of the molecule on the surface as well. So these things are all really useful for our studies. So just a couple more pictures of like what these things look like. So this is the one that's under a car park in Aarhus. So this is what this beamline looks like. This is a synchrotron, but this one here actually is not a synchrotron. It's just a sort of standalone XPS kit. So you can do XPS just with a normal X-ray source. It doesn't have to be at a synchrotron facility. It's less intense, so you don't take measurements as quickly, but you can do it just on a sort of standalone kit. So this one is actually at Henry Royce facilities in Manchester. And then I mentioned obviously at the start that I was looking at CO2 capture. And so you might kind of think, well, how do I study gases if my chamber is at ultra high vacuum and I've got to pump all of the gas out of it? Well, what we use here are these facilities where it allows you to do XPS, but you can do it at higher pressures. So this is quite a recent advancement in the last sort of 10 years where advancements in like electron optics actually now allow us to do these measurements at higher pressures. And so now you can introduce gas up to like a few millibar, and then you can actually look at how the gas is interacting with your surface. So you can obviously let in things like CO2, or you can let water vapor into your chamber. And so this allows the study of more realistic environments, because obviously studying surfaces under ultra high vacuum isn't really that relevant for everyday life because we don't live in a vacuum. So this is now allowing us to actually look at more realistic environments for our surfaces. And so these are some of the beamlines that I've been to where we can do these, introduce these gases. So again, we've got the Henry Boyce facilities, the one that's in Sweden, and Diamond Light Source. So you have to apply for time to go to these facilities. So you have to write like an application, and then you don't always win the time because they're quite competitive. But yeah, you basically put in a bid to do your research at these facilities. So, okay, now I'm going to have another little detour onto the sorts of materials that I'm using here. So this is ionic liquids. Now, ionic liquids, they're essentially salts. So if you think about sodium chloride, where you've got a positive and a negative ion, this is quite similar. So we've got a positive and a negative ion. So here's a couple of examples of some of these ions. But because they're big and bulky, they don't pack nicely into a crystal like salt does. So they tend, instead of being crystals, they tend to be liquid and over a wide temperature range. But they are highly structured compared to most liquids because they've got this Coulomb interaction between the positive and negative charges. And so you can tune the properties of these by having different combinations of these ions, and there's millions of possible combinations. These also have what's called an ultra-low vapor pressure. So normally with a liquid, if you put it inside a vacuum chamber, it would just evaporate. But because these have what's called an ultra-low vapor pressure, you can put these into a vacuum chamber and they won't evaporate. So this is a picture of an ionic liquid inside, in an ultra-high vacuum chamber, just sitting there, bubbling a little bit because there's some water in there that's coming out. So this makes them really useful for studying using surface science techniques. So ionic liquids actually have loads of different applications. So today I'm talking about CO2 capture and also about photovoltaic devices, but they're also being investigated for batteries, catalysis, also lubrication. So for lubrication, actually, because they don't evaporate in ultra high vacuum, you can actually use ionic liquids as lubricants on spacecraft, where basically in space applications where that these things are going to be under vacuum. In vacuum, you can actually use ionic liquids as lubricants because they won't evaporate in those harsh conditions. You can also use them to grow nano materials. So these are actually some nanotubes that we grew in the lab. These are kind of like looking down on these kind of long tubes. So they've got loads of different applications. So I'm going to be talking about CO2 capture and solar cells. So okay then, so to start with them, let's talk about CO2 capture. So with CO2 capture materials, the currently used technology is alkanolamines. So these are known as amine scrubbers. So basically this is just some liquid that it reacts with the CO2 to form carbamates. So I don't know how many of you like chemistry. I have to do quite a bit of chemistry. My area of research is quite kind of borderline between physics and chemistry, but I always have to ask the chemist because my knowledge isn't that good either. But yeah, you get these carbamates formed in a reaction. So basically the CO2 molecule is here, and then this sticks to a nitrogen atom. in the alkanolamine and forms this bond, which is called a carbamate bond. But this is quite a nasty reaction, and so you actually need inhibitors to control the corrosion in the pipelines. And then if you want to regenerate this solution so that you can use it again, so you want to heat it up to get the CO2 out to store it somewhere, and then you want to use that liquid again, then you have to heat it very hot to get the CO2 out. So that's like 100 to 140 degrees. So all of that significantly increases the energy requirements of the plant, and so it makes it very costly. So obviously we want some cheaper methods of capturing CO2. So this picture here shows there's all sorts of different things being investigated for CO2 capture. So we need some smarter materials, and the one that I'm talking about here is ionic liquids. So what makes ionic liquids suitable for CO2 capture? For starters, they're non-flammable, which is always good when you're going to have lots of a liquid in this kind of environment. You can tune them to absorb particular gases or to separate certain gases. Like I say, there's so many different combinations of ions that you can tune them to do all sorts of different things. Generally, they require lower temperatures to regenerate them. So to like get the CO2 out to be able to use it again. And so some computational studies have shown that ionic liquids can reduce the energy consumption of a plant by 30% compared to the methyl, the MEA, as it's called. The other thing is that you can tune the interaction with the CO2. So you get what's called chemisorption, where you actually form a physical bond, a chemical bond, but you can also get physisorption, where you kind of get more of this kind of weak bonding between the CO2 and the ionic liquid as well. Some of the problems, though, I mean, because you're trying to capture CO2, but there are other gases in the flue stream coming out of the chimney. And so you have to be kind of mindful of all these other gases and how they interact with the ionic liquid. And so sometimes the presence of water and other gases has been shown to reduce the uptake of CO2. So that can be a bit of a problem. So I'm just going to show you, I'm not going to go into too much into my research, but I've got a couple of slides here showing you some of the research that I've been doing with these ionic liquids. So the ionic liquid that I'm using here is it's quite a complicated one. It's called P66614 benzene. So the P6614 is the positive ion. It's got a phosphorus in the middle and all these carbons around it. So it looks like this. And then the negative ion has got these kind of two ring structures, and we've got these two nitrogen atoms in there. So when this reacts with CO2, it's actually the benzene ion that reacts with the CO2. So the CO2 sticks to one of these nitrogen atoms. And that creates a carbamate bond, like the one I showed you before with the amine scrubber. The positive ion here actually doesn't react with the CO2, but it does influence how strong the CO2 bonds to the benzene. So it does kind of influence that strength of binding. So it does play some role here. So what we find when we look at this, so these are our XPS scans. So basically what you got, I said that we have to find out the binding energy of the electrons. So this is a scale showing our binding energy, and we're looking particularly at the nitrogen atom here. So basically we're looking at the nitrogen atoms in the benzene and then the nitrogen atom when it's bonded to the CO2. So I won't go through what each of these peaks mean, but you can see here at the bottom, the black peak, this is before we've exposed our liquid to CO2. We then introduce CO2 into our chamber, and we can see the shape changes dramatically. So this higher energy peak here comes up, and that is showing this bond here. So it's showing this carbamate bond that's forming when it reacts with the CO2. And then simply just by pumping the CO2 back out of the chamber, it does then go back to its initial shape. So if you overlay them, you can see that the black and the yellow ones before and after the CO2 are pretty much the same. So what it showed is that we can actually reverse the reaction just by pumping the CO2 out, so that it's not a bond that you can't break. You know, it forms this bond, and then we just pump the gas out and it comes back out again. We also did some measurements where we introduced water as well, and we found that the CO2 uptake didn't seem to be inhibited by the water in this case. It seemed to uptake the same amount of CO2. So we did a some similar measurements with a different ionic liquid here, where we've got P6614, so it's the same positive ion, but a different negative ion here. It's called tris. And this has got 3 nitrogens in, which it turns out is very complicated when you go to analyze this. And then we were like, this was a terrible idea. Why did we do this? So there's so many different nitrogen environments going on. So I mentioned when I talked about XPS how you can detect all these slightly different environments that the atoms are in. And so all these slightly different environments here come up as peaks. So we now end up with a lot of peaks. But what we find here is that, so we react this with CO2 again, and we also did some measurements with water again. So, water is present in the flue stream, so we wanted to see how it interacts with water as well. And what we found by doing a study where we changed the sensitivity of the measurements. So we had some very surface sensitive measurements, and then we probed a little bit deeper to look at like a little bit more of the bulk compared to the surface layers of the material. And what we found is that we get the CO2 goes deeper into the ionic liquid. And so we actually find that there's more CO2 absorbing in the deeper layers. Whereas when we expose it just to water, we actually find that most of the water actually sits at the surface and it doesn't actually go into the ionic liquid very deeply. It kind of just sits there at the surface. So this is, just kind of basically figuring out what is actually going on with how these ionic liquids react with the different gases. And so, I mean, effectively here, it's kind of separating them because the water sits at the surface and the CO2 goes deeper into the liquid. So, yes, we from our measurements then, so this is just a little summary about my research into CO2 capture. Using the techniques that we use, we're able to identify chemical reactions at our sort of liquid gas interface. We can determine whether they're reversible. There's another technique that we do where we can actually work out how the ionic liquid kind of orders. So we discovered that when you expose it to gas, the molecules in the ionic liquid kind of reorder themselves as the gas goes in. We can also study competitive absorption between the different gases. And so we have looked at other gases as well as CO2 and water. And you can kind of identify how deep into the liquids these gases go, so what depths they reside in the liquids. So it's all kind of increasing our understanding of how the CO2 capture materials work. So, okay, I'm going to go on to talk about solar cells. So, okay, this is a diagram which is always updated on the NREL website. So if you're interested in this, if you type in NREL efficiency chart, you can look at this in more detail. So this basically shows the how the efficiencies of different types of solar cells have been increasing since the 1970s. And it basically shows all the kind of record efficiencies. So you might look at these efficiencies here and you might think these are all very low. So, I mean, these are kind of going from like 13 up, mostly up until about 30%. So this is actually because solar cells are just inherently not really that efficient. And this is something called the Shockley-Queisser limit. So if you're interested, Google Shockley-Queisser and you can learn a bit more about it. This is the maximum theoretical efficiency of what we call a single junction solar cell, and that's 34%. So that's the maximum theoretical efficiency you could get from a single junction solar cell. So that's why these are all under around 30%. So this is because you basically with if you, I think you might know a little bit about semiconductors. In a semiconductor, you've got what's called a valence band and a conduction band. So if you think about your electrons, you've basically got some electrons which are filled up to a certain point, and then you've got like an empty band which you can then excite these electrons into. And if you do that, you need a particular energy to excite from your valence band to your conduction band. And so when you think about the light coming from the sun, you've got a whole range of wavelengths. And if the light coming from the sun is, if the energy of a particular photon is too low to excite that transition, then it just won't happen. Whereas if your photon coming from the sun has too much energy, then it will excite that transition, but then it'll have some wasted energy. And so basically, if, like I say, you can read a bit more about the Shockley-Queisser limit, but it's basically that most of the solar spectrum is actually wasted because it's only one particular energy that is going to excite that transition between the valence band and the conduction band for your particular material. And so most of that solar spectrum is wasted, and that's why we only get a theoretical efficiency of 34%. So just to talk you through this then, we've got the standard solar cell that you would see on people's rooftops are the silicon solar cells, and these are in blue, and you can see that these have been going since the 1970s, and the efficiencies of those hasn't really increased much. You've got these things called multi-junction solar cells, which I'll talk more about in a minute, but they are very expensive, and they are the most efficient ones, but they're not suitable for commercial use because they're too expensive to make. You've got things like emerging photovoltaics. So I'm going to be talking to you about perovskite cells, which are these ones here, which have got like the yellow circles that are surrounded by the red line. And so these are quite a recent discovery, and the efficiencies of these have been increasing massively. And also hybrid ones, perovskite silicon ones, where they basically put a perovskite material on top of a normal silicon cell, and these efficiencies are doing really well as well. So I'll talk you through a few of these. So your standard silicon solar cell then, so I already just said this and mentioned this to you about how you are exciting from a valence band to a conduction band. So this is this picture here. So you've got like a valence band and you've got a conduction band, and your incoming light is exciting an electron across that gap, and it's leaving behind what we call a hole. So it's like the absence of an electron, if you like. So solar cells are based on what's called a PN junction, which is it sounds very fancy, but basically it's just a piece of silicon that has been doped in an interesting way. So basically you get your silicon, which is a semiconductor, and you imagine taking away some of those silicon atoms and replacing them with a different type of atom, which behaves a little bit differently. And so what you get here is an N-type semiconductor, or N-type silicon, which basically you've introduced some atoms that have got an excess of electrons. So now what you have are these excess electrons on this side. So then you take your piece of silicon and you dope it with some different types of atoms. So you, again, take away some of the silicon ones and put in their position this different type of atom, which now leaves you with a lack of electrons, or holes. And then essentially when you put these two pieces of material together, you get what's called a PN junction. And this creates an electric field at the interface between the two. And this is because these electrons and holes start kind of crossing over into each other and recombining, and this results in this electric field. And so when you get your light coming in from the sun, you excite an electron from your valence band to your conduction band, but because you've now got this electric field, that then separates your electron and your hole, and that is what drives the current in your solar cell. So essentially, whenever you've got a photovoltaic device, you're always using the sun's energy to generate an electron and a hole, and then you're separating those with an electric field. So that's what happens here, and this is just your standard PN junction. So that they're fairly efficient, according to our Shockley-Queisser limit of 34%. This 27% is pretty decent, but you do need to grow some large single crystals, and they can be a bit pricey to make. I mentioned these multi-junction solar cells. So now, what I just said about the PN junction, imagine doing that, but now you take lots of PN junctions and you pile them all up on top of each other. And what you do is you choose these materials. So each of these materials absorbs a different wavelength of light. So now this is how you beat the Shockley-Queisser limit. Because if you only have one junction, it can only absorb one particular wavelength of light. But now you've got lots of these junctions, and each of them you can you can make it a different material which will absorb a different wavelength. So now you're making use of a whole spread of wavelengths of light coming from the sun. So the theoretical limit for a cell with an infinite number of junctions would actually be 86%. You'd still get, there's still some loss processes involved there. Obviously, you're never actually you can't build a cell with an infinite number of junctions. But yeah, that just gives you an idea of, even if you just got a lot of PN junctions, you're still not going to get anywhere near 100% efficiency with solar cells. Like I said, these are very expensive to produce, so they're not realistic for everyday use. So during my PhD, I studied something called dye-sensitized solar cells. So these work a little bit differently. So instead of having a semiconductor that absorbs the sun's light, you actually have a dye. So this is a dye molecule, and that absorbs the sun's light, and you get this, within the molecule, you get an electron being excited within the molecule to a higher level. And then again, it works the same way as before. So now you've generated an electron, you've generated a hole, and then you just separate them using an electric field. And so your electron goes off into this material that's called an electron transport layer, and your hole goes off into this hole transport layer, and you separate these charges, and that's what drives your current. So this is based on this dye, and it's between these two different types of these N-type or P-type materials, which separates your charges. So these are very cheap to manufacture, but they are only about 13% efficient. And there was quite a lot of work on these in the sort of 90s and into the early 2000s, but nobody could ever really find another molecule which worked quite as well as the original one. So they've never really taken off that much. But I do think you can. I was at one point, I know you could buy these things, but yeah, they're not massively efficient. So the one that I'm going to share a little bit of research with you about today is perovskite solar cells. So with these, it's a little bit similar to the dye-sensitized solar cell. So now, instead of the dye absorbing the light, you've got this perovskite material which absorbs the light from the sun. So this is the what harvests the sun's light. This is what absorbs the light. So perovskite structure has this structure ABX3. So A is this atom in the middle, which is some organic molecule. B is usually lead, although lead is toxic, so there are some efforts to try to remove lead and to replace it with something that's not toxic. And then X, the orange ones, are halide, so something like chlorine or bromine or iodine, or you can have a mixture. So the one that we were looking at was called methyl ammonium lead iodide chloride. So the organic bit is this molecule here, where you've got this CN bond, and then we had a mixture of iodine and chlorine in there. And then what you do is you take your perovskite material, ABX3, and you put it again between two materials that are going to help you to extract your charges. So you've got the material, the ETL, the electron transport layer, that helps to extract the electron, and your hole transport layer that extracts your hole. And so in the work that I'm going to show you, we were looking at perovskites on tin oxide. So our tin oxide was our electron transport layer. So the efficiencies of these things, they started off only like 3% efficient in 2009, and now they're over 27% efficient. So the efficiencies are going up massively, but they're still not, we can't commercialize them because they are still very unstable. So the problem is that the perovskite degrades very quickly. It's unstable under high temperature and humidity, which isn't ideal when you're planning to put these things outside where they're likely to get hot and humid. So obviously there needs to be more work on these to stabilize them before they can be commercialized. So the work that we did then fairly recently, we looked at introducing ionic liquids into the perovskite structure to try to help stabilize it. So there had been some work showing that ionic liquids can improve the efficiency of the perovskite devices. So we wanted to look in more detail about what's actually happening on a fundamental level. So what we did is we used the same positive ion, which this one's called BMIM, And then we changed the negative ion. So we tried BMIM BF4 and BMIM chloride. So basically changing out the negative ion to see what effect that had. And then we looked at what happens when we deposit these, the perovskite ionic liquid mixture onto a tin oxide layer. And we were basically just trying to study the stability of them and how these things degrade when we expose it to heat and moisture. So we heated the sample up and we also exposed it to water vapor. So we basically had a few samples here. We had just the pure perovskite with and without the tin oxide layer, and then we had the perovskite mixed with the BMIM BF4 and the perovskite mixed with the BMIM chloride, again with and without the tin oxide. So again, I'm not going to tell you what every peak here means, but what we've got here are we've got two samples. One is a very fresh perovskite film. So this is just pure perovskite to start with, without the ionic liquids. We've got a very fresh perovskite film that we literally deposited and put straight into the experiment. And then we've got what we call an aged one, which was about a week old. So we made it about a week before, and we actually did store it in very careful conditions under a nitrogen environment. But as we will see, it is actually heavily degraded after just a week. So what we're looking for here is this particular peak. So the green peak here is what we want. This is that CN bond in the perovskite, and that means that the perovskite is in the condition that we want it to be in. And so in the fresh sample, you can see we've got lots of that, whereas in the aged sample, you can see there's not very much of it, and that is because the perovskite has decomposed. So it decomposes. So here's some more chemistry for anybody who likes a bit of chemistry. It decomposes, and the lead from the actual perovskite structure ends up coming out of that structure and forming lead iodide. And then both of these products here can go on to degrade further. And so you can actually get degradation all the way to metallic lead. So so a lot of these other peaks, particularly in the aged one, are due to the decomposition products. So this one that's a week old is already quite heavily decomposed. So then we're looking at the ones with the ionic liquid as well. So here we're looking at the nitrogen atoms. And again, we're looking here at the green, the green peak is the one that we want. This is this CN bond in the perovskite structure. And we can see with the fresh perovskite, we've got lots of that. Whereas with the aged perovskite, there's very little of that. So in fact, most of the nitrogen has just completely gone from the aged perovskite. But if we now look at the ones where we've mixed the perovskite with the ionic liquid, these are actually a week old. So we made these at the same time as the aged perovskite and stored them in the same conditions. The only difference is that these have got the ionic liquid mixed in with the perovskite. And you can see that the ionic liquid has protected the perovskite from degradation. And so you still got lots of this green peak that we want. The blue peak is the degradation peak that we don't want. And we can see that there's very little of that really with the ionic liquid. The orange peak is actually inherent to the ionic liquid itself. So that's fine. That's just part of the ionic liquid. In these measurements, we were actually exposing the samples to water to see what happened when we exposed them to water vapor. And actually not a lot. Well, there's some slight changes. So when we expose it to water, we do see some changes in the shape of the spectra. So there might be some like rearrangement going on of the structure as we put the water in. But when we pump it back out, it actually just seems to go back to how it was. So there didn't seem to be any particular damage to it whilst we exposed it to water. So what we see is that the ionic liquids protect our perovskite from degradation. And then this is just some data from the lead, because I mentioned that you can actually get degradation all the way to metallic lead. And so for our aged film, when we exposed it to water, so during the actual exposure to water process, we actually saw this extra peak coming up. And this is actually the decomposition of the perovskite into metallic lead, which is like the final stage of decomposition. So this is now very heavily decomposed at this point. But our ionic liquids are fine. We don't see any degradation of the perovskite when it's mixed with the ionic liquid. So again, it's showing that this does protect the films. So, okay, a little summary then of, so I'm at the end now, a little summary of ionic liquid modified perovskite films. So we found actually that the Beeman BF4 formed a protective layer over the perovskite. So like I say, I've not shown all the data here. The ionic liquids protect the perovskite films from degradation. And we also found that the tin oxide did enhance the stability of the perovskites as well. So yeah, this is a project that's ongoing. So I've got a PhD student at the moment who is continuing with this research. So just a slide then about the outlook on CO2 capture and solar energy materials. So for CO2 capture, there's lots of materials being investigated for CO2 capture, and it's about trying to do it in a smarter way where we can control gas absorption and separation on a molecular level. But we need to consider the cost to regenerate the gas capture materials, and always we have to think about what chemicals are being used or produced in any of these reactions. With the solar energy, every year we see advances in the efficiencies of photovoltaic devices, but we do need to consider, again, the stability of them, sustainability as well, and environmental issues. So I mentioned the lead in the perovskite. Ideally, we don't want to be making solar cells with lead in them, because then that's an issue with how do we dispose of those afterwards. So ideally we want to replace that lead with something else. So we always have to consider all these different issues about stability, sustainability, etc. So okay, then I've just got some acknowledgements. So these three guys here are my former PhD students who did this work. Sergey is a chemist, a crazy chemist here at Lancashire. And then I also work with people at Manchester University, and these are some of the beamline scientists and scientists at the Henry Royce facilities that I work with, and a bunch of funders there. So yeah, that's the end of my talk. So thank you very much for your attention.
Hey, hi everybody. I'm Dr. John Fletcher. I'm an astrophysicist here at the university. I'm going to lead the Q&A session now for Karen. So Karen, the first question so if you do have any questions, please feel free to post them in the Q&A chat function, and I will read them out to Karen so she can answer them, and I'll publish them in the Q&A chat as well. So the first question we've had through Karen is, in the second slide on the ionic liquid using TRIZ, what is the difference between the C1 graphs on the left and the N graphs on the right, and what does it mean?
Okay, right. Can I might have to share my slide again. Hang on. Right, can you see the slides moving?
Yep.
Okay, so which one was it again? Sorry, was it the CO2 capture
slide? The second slide on the ionic liquid. So the difference between the C1 graphs and the N graphs.
Was it this one, do we think?
Yes, I'd say that one.
Yeah, let me just, it could be the other one. Yeah. So the difference here, like I didn't really have much time to kind of explain them, but basically the carbon 1s, so this is looking particularly at the carbon atoms in the molecules. So here with the carbon, you're basically seeing any environment which is from any of these carbon atoms. And so in fact the big peak here, hang on, let me get a pointer thing going. The big peak here is actually mostly from these carbon atoms in the positive ion, because you've got, if you add these up, you've got loads of carbon atoms there, and so that's actually contributing to that main peak. But the little peak here that says carbamate, that is due to this bond here. So it's actually from the CO2 that's stuck to the negative ion. Whereas the nitrogen 1s here is looking specifically at these two nitrogen atoms. And so then this is basically showing you what's going on with the different environments with these nitrogen atoms, which are actually really difficult to understand, because in theory you've only got two nitrogen atoms here, but we end up kind of with three peaks. So it kind of took us a while to try and kind of figure out how we could kind of explain it. I mean, we kind of, in theory, these two nitrogen atoms here are chemically equivalent, so that would form one of your peaks, which would be this. And then once the CO2 sticks to this one, these are now in two slightly different environments, which are actually now a little bit different to the initial one. So that's how we kind of end up with three. But yeah, anyway, I guess it's a little bit difficult to explain without going into too much detail about XPS. Does that kind of answer the question?
Thank you, Karen. So whilst I'm waiting to see if there's any more questions to come through, do you think the solar cells that you are looking at, the perovskite materials, do you think they're the next generation then of solar cells? And what efficiency do you hope to be able to get them to?
Yeah, I mean that realistically, they're not going to be more efficient than the silicon ones, right? I mean, it's so you might get them to say 30% or something, but the point is that they are cheaper to make than the silicon solar cells. With any of these different types of solar cells, it's a trade-off, you know, between how efficient they are and how much they cost to make, and also other things like how it, you know, how you would recycle them afterwards and things like that. So yeah, I mean, they probably might reach a similar efficiency to the silicon ones, but the key thing is that we need to get them stable to even be able to do that. There is a lot of interest in the hybrid ones as well. I can't really change the slide without sharing my screen again, but the ones where you basically have a silicon solar cell and then you put the perovskite layer on the top, because that's like a multi-junction one, because now you've got the silicon, which absorbs one wavelength of light, and then you've got the perovskite layer, which then absorbs a different wavelength of light. So you're now covering more of the solar spectrum. And so they're showing really good efficiencies. So it might be that might actually be quite a promising path for the hybrid silicon perovskite ones, I think.
Oh, sorry, I think I lost Karen a little bit then. I'm not sure whether that was me or Karen. Hopefully it's...
All right, can you still hear me?
Maybe it's me. Karen, are you back? I think everything just froze a little bit for me.
All right, I'm here. Can you hear me?
Yeah, I can hear you. Okay, maybe it's at my end then. That's fine. So with the facilities that you use to go and test all these materials, do you actually get to use them? Like you showed in some of the photos, there's people in white lab coats kind of hands in the machines. Is that what you do, or are you kind of sat in a room at the side on a computer, not touching anything because they won't let you? How does it work?
Mostly it's us doing it. Yeah, it depends which facility you go to. So the one actually that you're probably referring to was one of my students in a white coat in Denmark. With that one, they just leave you to it. They just go off and you don't see them for so the beamline scientists just make sure you're all right, and then they just go, and then you're literally up ladders, you're you know, putting things in and out of the chamber, letting gases in.
So it's very hands-on.
Very hands-on, but then at some facilities you go to, they're a bit less hands-on because they kind of they don't want you breaking their equipment because they've got such a busy schedule of users coming to use the facility. If you do something and you damage it, then that's going to throw all of their schedule out. So they do still let you do stuff, but it depends how much they trust you.
A bit more controlled.
A little bit more control. And also I think some of the newer facilities, everything is very computer controlled. So like if you want to change the position of your sample, you can just type it in on the computer and it'll change it. Whereas that one in Denmark, it's very old school. So if you want to change your sample, you've got to climb up a ladder. You've got to twiddle some nods and you got to, you know, yeah. So which is kind of more fun, really, isn't it? But,
so it's to do with the technology, then, I guess, that you're doing.
Kind of.
Yeah. And you mentioned your students there in one of the photos. What kind of, say, final year BSc projects or MSc projects do you offer kind of around your research? What type of things will the students be doing? You know, will they be in the lab with these samples, or like what does it look like?
I mean, obviously we can't go to a synchrotron facility during you know, a final year project, but sometimes I've got a project at the moment where I get them doing computational modeling of photovoltaics, so they can use computational simulations to try and work out, what combinations of materials would give, good efficiencies. And then I do also run like experimental ones. I have in the past done ones where we try to build a device using the dye sensitized solar cells that I mentioned. And I've also got one, I showed those nanotubes where you can grow nanostructures using ionic liquids. So that was actually from a BSc project where they grew these titanium dioxide nanotubes using ionic liquids in this kind of electrochemical cell. So yes, that was from a project.
Sounds really interesting. So you mentioned as well in the talk about the advances that we've made in the past decade in this field. Where do you see the next decade? Where are the advances? What would you like to see? I think obviously you've already mentioned about the solar cells that you've been kind of looking at and them being more affordable, because obviously from a, if you're a homeowner, if you want to have kind of cheaper energy, then that's a big thing. But what other advances maybe within the industry, within the technology, do you need for the next decade?
Yeah, it's a good question. I mean, because the thing is that there always seems to be something new coming up. Because I mean, when I started my PhD, the dye sensitized solar cells had just been discovered, and so that was like the latest thing. And then now, of course, the last few years, it's been the perovskite solar cells. So now there's a big drive there. So it wouldn't really surprise me if there was just something completely new that we couldn't even anticipate, that somebody would just invent, and suddenly it's like, oh, this could be the next big thing. So yeah, it's difficult to say really. I mean, as I said, I do think there is some scope in the perovskites. Maybe those hybrid ones might be might be the way to go. I mean, in terms of things like the CO2 capture as well. I mean, hopefully we're going to be kind of phasing out the production of CO2 anyway. But in the meantime, I guess there's going to be a big drive to try and use some of these new technologies to capture CO2. Whilst we try to develop some new greener energy sources. Yeah, I mean, I think really it's kind of see where we go with what technology there is, and see if anybody comes up with anything else that's a little bit mad and crazy.
Okay, well, I'm conscious that we're just coming up to 2:30 and that people may have other lectures and things to get off to. So if you do have any more questions, feel free to email us, and then we can get back to you if you think of any questions. And if there are no more to be popped up in the chat, then I'll just say thank you very much to Karen again. It's been really interesting. It's outside my field of research, so it's always nice to hear what else is going on within the Jeremiah Horrocks Institute. Thank you all for coming, and we hope to see you again soon at the next one. Thank you.
Thanks, everyone. Bye.